students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 3, which is a chemical reaction equilibria. So in this lecture, we are going to discuss about the effect of temperature on equilibrium constant that denoted by K. Then we are going to discuss about the effect of pressure on equilibrium constant, and then after finally we are going to discuss about the feasibility of any reaction. In previous lecture discussed about the standard state gives free energy that denoted by delta G naught, which is equal to minus RT ln K, which is the most important equation in point of view of exam. So we already discussed about this equation and already discussed about the ln K, or can say that equilibrium constant K, and definition of K that can be given by K is equal to capital pi of AI whole raised to VI, where capital pi, which meaning is a multiplication of AI like this, A1 into A2 into A3 and so on. So we are going to multiply ith component with each other. If I am going to say capital pi of AI, which meaning A1 into A2 into A3 and so on. Vi, which is a stoichiometric number for that particular component I, and A, which is our activity. We know that activity, which is a relative fugacity, which means fugacity in standard state of I component upon fugacity at standard state of I component pi as it is, and whole raised to Vi, which means stoichiometric number of that particular component. So here we are going to discuss about the effect of temperature on equilibrium constant. So what is the effect of temperature? If I am going to increase the temperature, then what the behavior of equilibrium constant, we are going to discuss in this lecture. So let's first start with the effect of temperature on equilibrium constant. So equilibrium constant that denoted by capital K. We already derived the effect of temperature on chemical potential in lecture number 23 of this CET2. So using the equation of effect of temperature on chemical potential that denoted by d of mu naught upon T upon dt is equal to minus enthalpy change at standard state upon T square. So this is the equation for the effect of temperature on chemical potential. But we know that at standard state this mu naught is equal to G naught. So can say that mu naught is equal to G naught. So this equation can be written like this: d of G naught upon T upon dt is equal to minus delta H naught upon T square. So we can replace the chemical potential by the give free energy. Now dividing this let's suppose this is our equation number 2. Now dividing this equation number 2 with constant R, we may get, so if we are going to dividing this equation number 2 with R, so let's write here dividing equation 2 with capital R, which is our guessed universal constant. Okay, so that equation becomes d of G naught upon RT, okay, upon dt is equal to minus delta H naught I upon RT square. Here I am going to divide with R, so I can write this R to here G naught upon RT. So here I write G naught upon RT, and here again I have to divide with 1 upon R, so it becomes delta H naught upon RT square. So it becomes delta H naught upon RT square. Now, if rearranging this equation and let's put the value of ln k. In previous lecture, we derived the value of delta G naught is equal to minus RT ln k. Okay, so I'm taking this RT to this side, so it becomes delta G naught upon RT. So it becomes minus ln k is equal to delta G naught upon RT. So I can replace this G naught upon RT with minus ln k. So if I am going to replace this and putting the value of minus ln k here, so our equation becomes like this: d of this minus ln k upon dt is equal to minus delta H naught upon RT square. Now this minus minus cancels, so it becomes d ln k upon dt is equal to delta H naught upon RT square. So this becomes our effect of temperature on equilibrium constant. So what we have to do, first we are considering the effect of temperature on chemical potential. Equation for that is already derived in lecture number 23. Using that equation, that can be given by d of delta d of mu naught upon t upon dt is equal to minus delta H naught upon t square. Now we can replace this mu chemical potential with the Gibbs free energy, because we know that G bar is equal to mu. So can say that G naught is equal to mu naught. We can write this at standard state. Okay. So I am just replacing this mu naught with G naught. So that equation becomes like this. Now I want to know about the effect of temperature on equilibrium constant. So I have to put the equilibrium constant here. Okay. So to make the equilibrium constant equation, I have to divide with 1 upon R. Okay, so this equation number 2. So if I am going to divide with 1 upon R, this equation becomes like this. So I can easily replace G naught upon RT with minus ln k. So I am just putting the value of the minus ln k here, and this equation becomes like this. So this equation is known as the effect of temperature on equilibrium constant, and this equation is also known as a one Hoff equation. Okay, so in exam question may ask like write down the effect of temperature on equilibrium constant or derive the one Hoff equation. Okay, one Hoff equation. So it's also known as the one Hoff equation. So this is just a numerical or equation point of view of effect of temperature on equilibrium constant. Now let's understand what is actual effect of temperature on equilibrium constant. For the understand effect of temperature on equilibrium constant, let's consider this equation. In this equation, value of delta H. Let's first write this equation here so we can easily understand. So d ln k upon dt is equal to delta H naught upon RT square. Delta H naught upon RT square. Okay. So we cannot directly predict the effect of temperature on this equilibrium constant. It depends on delta H naught, or can say that value of delta H naught. If value of delta H naught is a negative, then can say that reaction is a exothermic. If the value of delta H naught is a negative, which means the reaction is a exothermic reaction, which means a reaction that liberate energy, or a reaction that liberate energy from the system to surrounding. That type of reaction is known as a exothermic reaction. So for the exothermic reaction, value of delta H naught, if the value of delta H naught is a negative, so can say that reaction is a exothermic. Now if reaction is the exothermic, which means energy is liberated by the reaction. Now if I am going to increase the temperature, then what happens? So let's suppose there will be reaction A plus B gives C, and it's a liberate the energy during the reaction, which means this reaction does not require heat. That's why this reaction liberating heat. Okay. Now if I am going to apply heat to this reaction, what happens? This reaction already liberating heat because this reaction does not require heat, and I am going to apply the heat by increasing the temperature. Equilibrium constant will be decreased. So if I am going to increase the temperature in a exothermic reaction, or can I say that when value of delta H naught is a negative, then if I am going to increase the temperature, value of K or equilibrium constant will be decreased. Now for endothermic reaction, or can say that when the value of delta H naught is a positive, at that time that reaction is known as a endothermic reaction, which means a reaction which require heat. Okay, this reaction, let's suppose again this reaction which require heat. So if I am going to apply the heat to this reaction, and this reaction already want heat, so what happen, the equilibrium constant will be increased for this reaction. If I am going to increase the temperature for endothermic reaction, in endothermic reaction require heat. That's why if I am going to increase the temperature, apply the heat on the reaction, equilibrium constant will be increased. So this is a theoretically we can say that if in a endothermic reaction, if we are going to increase the temperature, that will be increase the K. Similarly, we can put the value of this delta H in negative sign in this equation and increase the temperature, value of K will be decreased, and similarly for the exothermic reaction. So we can understand from point of view of this equation also, and we can also considering this theoretical basis of equilibrium constant. So this is about the how the effect of temperature on equilibrium constant. Now let's discuss about the effect of pressure on equilibrium constant. Okay. So we know that equilibrium constant K is related to the standard Gibbs free energy change, and the equation of that can be given by G naught is equal to minus RT ln K. At constant temperature, there will be a no change in minus delta G naught upon RT. Okay, so this is the equation for the equilibrium constant. At the standard temperature, there will be no effect of pressure. So here I am writing no effect of pressure. Remember that there is a no effect of pressure on equilibrium constant. So there is a no effect of pressure in equilibrium constant at constant temperature, because if I am going to take constant temperature, there will be no effect of pressure on equilibrium constant, because there is no directly connected with the pressure. In equation we can see that there is a no pressure in this equation, so there will be a no effect of pressure on equilibrium constant. But remember that there will be a effect of pressure on equilibrium conversion. So that is a different question that may be asked in exam. We will discuss about that. What is the effect of pressure on equilibrium conversion? Both are different questions, so don't be confused between the effect of pressure on equilibrium constant and effect of pressure on equilibrium conversion. Both are different things. Okay. So there will be a, here we are studying effect of pressure on equilibrium constant, and second thing is equilibrium conversion. We will discuss about this in a furthermore lecture. So there will be no effect of pressure on equilibrium constant. Now let discuss about the next topic, which is feasibility of reaction. Feasibility of reaction, which means any reaction is feasible or not. But before discuss about this, let discuss a more generalized equation for the this one-off equation, or can say that effect of temperature on equilibrium constant. So to find out the generalized equation of effect of temperature, let's first write this one-off equation. d ln k upon dt is equal to d ln k upon dt is equal to delta H naught upon RT. So this is our can say that one half equation, or can say that effect of temperature on equilibrium constant K. Okay. Now we are going to derive more generalized equation from this equation. So rearranging this equation, we will get d ln K is equal to delta H naught upon R into dt upon T square. Okay. So we are just taking this T2 this side. Here there will be a RT square. Okay. So this is equation of one term where RT square, so it becomes RT square. Okay. So we are just rearranging this equation. Now integrating this equation. So let's first integrate this above equation by integrating of this equation with k2 k dash and t2 t dash, we will get. So let's first integrate this equation with k to k dash. It will be like this: d ln k is equal to integration of t to t dash of delta h naught upon r into dt upon t square. So upper limit minus lower limit, so it becomes ln k minus ln ln k dash upon ln k is equal to, this will be a constant, so it becomes l delta h naught upon r, then integration of t to t dash dt upon t square. So again, if we are going to rearrange this equation and integrating of this term, it will be take minus. So we are just replacing the minus sign with rearranging this equation on this side. Okay. So rearranging equation on that side, it becomes ln k upon k dash is equal to minus delta h naught upon r 1 upon t minus 1 upon t dash. So we are just taking minus, so it will be becomes ln k minus ln k dash. So ln k minus k dash becomes like this, and integration of this becomes like this. Okay. So above equation is more generalized form of effect of temperature on equilibrium constant, and it's used to find out equilibrium constant from various temperature range. Okay, if we have the two temperature T1 and T2, then we can use this equation to find out the equilibrium constant from one equilibrium constant to second equilibrium constant. Okay, so this is a very important equation for point of view of exam. In also it's used in many numerical. So remember these both equations: one generalized form of one of equation, and second this one of equation. Both equations are used to find out the equilibrium constant and temperature in many numericals. Okay. So now let's discuss about the feasibility of reaction. Feasibility of reaction, which means any reaction is possible or not. From value of the standard free energy change, we can formulate an appropriate criteria for feasibility of chemical reaction. Before search for catalyst and other conditions, it is necessary to find out the reaction is possible or not. If the reaction is possible, then there is no point in pursuing a long and expensive experimental investigation in improving the rate of reaction. Okay, any reaction starting with the pure reactant will have a tendency to proceed to some extent at very slow and very small level. Okay, so there will be no meaning of before taking experiment we have to apply cost and expensive material and expensive catalyst. First we have to experiment and find out the criteria for the chemical reaction. So from the value of standard free energy change, we can formulate the approximate criteria for feasibility of reaction. Any reaction is feasible or not. If reaction is not possible, then there is no point of in pursuing purchase long and expensive experimental investigation on improving the rate of reaction. If there is a no standard state free energy deciding for the reaction, there will be a no any equipment will work on that reaction. So first we have to understand how the effect of energy, or can say that how the uh, gift free we can understand the equilibrium constant and gift free energy. Any reaction starting with the pure reactant will have tendency to produce some extent at very slow level and very small level. So any reaction starting with the pure reactant will have tendency to proceed some extent at very slow level and very small level. From the value of the equilibrium constant, we can relate the standard state gift free energy of reactant and value of standard state gift free energy gives the necessary information on thermodynamic possibility of the reaction. So even decomposition of water vapor to a hydrogen and oxygen will proceed to some extent under the atmospheric temperature and pressure. So in atmosphere there will be any water molecule that can also convert in H2 plus O2, but it is very at small level. So let's consider first that reaction. So that reaction that can be given by H2O give H2 plus 1 half O2. If we are going to do this reaction at by own, then there will be a large amount of energy is required, but this reaction is also happen in our environment by owing this by itself, but the rate of conversion of H2 and O2 is a very small, or can say that it's to take very long time to converting this H2 from H2O, or can say that H2 plus 1 half O2 from H2O. For this reaction, the equilibrium constant value K is equal to 1 multiplied by 10 raised to minus 14, which is a very small value. That means reaction is not thermodynamically feasible. So if the delta G is a negative, if the value of delta G is a negative, then value of K is greater than 1. So can say that reaction is a possible. Okay. So let's consider the our equation delta G naught is equal to minus RT ln K. Okay. So if the value of delta G naught is a negative, then K will be greater than 1. So reaction is a possible. If the value of delta G naught is a positive, then value of K is less than 1. So can say that reaction is not possible. Okay, but if the value of delta G naught is equal to 0, then value of K is equal to 1. So can say that reaction is a possible to considerable extent. We require one some external energy to start this reaction. So for that type of reaction, we can purchase the some catalyst and do the some reaction, and we can just change the favorable condition for that particular reaction. So value of G naught is negative, then reaction most favorable. If delta G naught is in case in positive direction and becomes less favorable. So what is value of G naught is required. So to understand this, delta G naught, if the value of delta G naught is less than 0, then a reaction is promising, okay, or favorable. So reaction is possible. In other language can say that reaction is a possible. If the value of delta G naught is between 0 to 40,000 kilojoule, then reaction quite be favorable or possible using some extent of energy. But if the value of delta G naught is greater than 40,000 kilojoule, then reaction is not thermodynamically possible. Okay. So if in some numerical given that reaction is possible or not, So first you have to find the value of delta G naught, and value of delta G naught is if we are getting the value of delta G naught more than 40,000 kilojoule, then we can say that that reaction is thermodynamically not possible. Okay, so this is how the if feasibility of reaction. So reaction possible, which means reaction is a feasible. Okay, if a value of delta G naught is a negative, then K greater than 1, so can say that reaction is a feasible or possible. Then delta G naught is a positive, then K is less than 1, the reaction is not feasible, and delta G naught is equal to 1, so can say that K is equal to 1. At that time reaction requires some amount of external energy or some extra work, okay, for the feasibility of reaction. So this is all about the today's lecture. I am completing my lecture here. Thank you.